You've been lied to about time, not by some conspiracy, not by scientists, philosophers, or even your teachers, but by your own brain. Every time you look at a clock, watch a sunset, or feel the drag of a long day, your mind is weaving a story about time that simply isn't true. We think of time as this invisible river, always flowing forward, carrying us from the past into the future. We imagine there's a universal now that everyone shares, ticking away second by second like a cosmic heartbeat. But none of that holds up under a microscope, not in physics, not in neuroscience, and not in reality. The deeper we dig, the stranger time gets. Einstein showed us that clocks tick differently depending on how fast you're moving or how close you are to a massive object. Quantum mechanics throws a wrench into cause and effect, and modern experiments suggest that time might not be a thing that moves at all. It might be something that emerges from something even more fundamental. This isn't just about bending your mind with cool science facts. It's about realizing that the very thing we base our entire lives on, schedules, memories, plans, aging, is based on assumptions that are, at best, incomplete. And at worst, completely wrong. So let's take everything you think you know about time and break it. Let's start with a basic assumption most of us never question. The idea that time is something that flows, that it moves forward in a straight line, dragging everything along with it. We say time flies, time marches on, we lose time, we waste time. All of these expressions rely on the same picture. That time is this invisible conveyor belt we're stuck on, and we're always being pulled from the past into the future, whether we like it or not. But here's where things get strange. Physics doesn't agree with this picture at all. In fact, if you look at the actual math behind how the universe works, whether it's classical mechanics, relativity, or even quantum theory, nowhere in those equations is there anything that actually flows. Time in physics isn't something that moves, it's something that just is, and that completely flips the way we're used to thinking about reality. Let's break that down. Start with classical mechanics, the kind of physics Isaac Newton developed. Newton imagined time as an absolute background. It was like a perfectly even stage on which all events happen. The clock ticks forward the same way for everyone, everywhere, and for a long time that idea worked fine. It matched our everyday experience and let scientists make precise predictions about how objects move. But it wasn't the whole story. Then Einstein came along. In his theory of special relativity, he showed that time isn't absolute at all. It's not the same for everyone. It depends on how fast you're moving. If someone is moving quickly relative to you, they will actually experience time differently. A second for them might not match a second for you. And it's not just a feeling, it's real. Their clocks tick slower compared to yours. And that's not science fiction, we've tested it. We've flown atomic clocks on airplanes and compared them with clocks on the ground. The ones in motion run slower. Just a little, but measurably. Then there's general relativity, which took it even further. It showed that time also changes depending on how close you are to a massive object. The stronger the gravity, the slower time moves. This means that someone standing at the base of a mountain ages more slowly than someone at the top. Again, the difference is tiny, but it's real and confirmed by experiment. It's even accounted for in GPS satellites. If we didn't adjust for the time difference caused by gravity and speed, GPS would be off by several kilometers every day. So what does this all mean? It means that there's no universal now. Two people in different locations, moving at different speeds, or under different gravitational fields, don't experience time the same way. There is no master clock that everyone syncs to. Everyone's timeline is slightly different, and those differences add up. That already shatters the idea of a single flowing time that applies to all of us equally. But it gets weirder, because if there's no universal now, then what exactly is the present? What does it even mean to say something is happening right now, if that's different for different people? Physicists have a way of dealing with this. They use something called the block universe model. Imagine all of space and time as one giant four-dimensional shape. In this view, the past, present, and future all coexist. Every event, your birth, your first day of school, what you had for lunch yesterday, what you'll do tomorrow, already exists somewhere in this block. You're not moving through time. You're moving in time as part of this static, unchanging structure. It's all already there, it's just that your consciousness is only aware of one small slice of it at a time. You think you're moving forward, but really, you're just experiencing each frame of the universe, like someone watching a movie one frame at a time, unaware that the rest of the film is already shot and sitting there waiting. This isn't just a theory, it's the logical consequence of Einstein's equations. They don't pick out a present moment. They don't care about a flow. All events exist equally. It's just our brains that experience them sequentially. Now let's talk about what it means when we say time passes. What is that really? If nothing in the equations requires time to pass, then where does that feeling come from? It comes from us, from the way our minds interpret change. We observe the world changing. We remember what things were like before. We predict what might happen next. Our memories form in one direction, and our brains arrange them into a timeline. That gives us the impression that there's a before and an after, a past and a future. But that's just a result of how we're wired. It doesn't mean time itself is moving. All it means is that we experience one frame after another, and our memories keep track of what came before. That's enough to convince us that time is flowing. Think about a flipbook animation. Each page shows a slightly different picture. When you flip through the pages, it looks like there's movement. But the pages themselves aren't moving. They're just static images. You're the one doing the flipping. In the same way, all the moments of your life might already exist. You're just flipping through them, frame by frame, without realizing that nothing is actually flowing. Some scientists take this even further. They argue that change itself might be an illusion, that everything that has happened or will happen is already encoded in the structure of the universe, and our perception of change is just the way we experience that structure from the inside. In other words, time doesn't move forward. We just move along a timeline that already exists. This idea is uncomfortable because it challenges so many things we take for granted. If the future is already there, does that mean we have no free will? If the past still exists somewhere in the block universe, can anything ever truly be gone? And if there's no flow, then why do we live as if every second is ticking away? These are hard questions, and they don't have easy answers. But what's clear is this: the way we normally think about time, as something that flows forward, moment by moment, isn't supported by physics. It's something our minds project onto reality. It helps us function, but it's not how the universe actually works. And once you understand that, it changes how you see everything. Time isn't a river, it's a map, a fixed landscape. You don't move through it, you exist within it. And the flow you feel, that's just your brain flipping through the pages. We often take the direction of time for granted. We wake up, get older, watch things fall apart, and never the other way around. Broken cups don't jump back together. People don't grow younger. Smoke doesn't return to a cigarette. Everything around us seems to point in one direction, from past to future. We call this the arrow of time, and it feels so obvious that we rarely question it. But when you start looking at the fundamental laws that govern the universe, that arrow suddenly looks less like a rule, and more like a strange exception. Let's start with physics again. At the level of fundamental particles, the equations that describe how things behave are time symmetric. That means they don't care whether time is running forward or backward. You can flip the direction of time in those equations, and everything still works. In other words, if you filmed a single particle bouncing around and then played the footage backward, the math wouldn't object. There's no built-in preference for time going one way. This is true in Newtonian mechanics, in electromagnetism, and even in quantum mechanics. The Schrödinger equation, which governs how quantum systems evolve, also works just fine in reverse. So where does the arrow of time come from? Why does everything in our experience point forward when the laws underneath don't care? The answer usually points to one thing: entropy. Entropy is a measure of disorder. A low entropy state is ordered and structured, like a neatly stacked deck of cards or a new pack of batteries. A high entropy state is messy and disordered, like a shuffled deck or drained batteries. And according to the second law of thermodynamics, entropy tends to increase over time. That's the rule that gives us the arrow of time. Systems move from order to disorder. Once an egg is scrambled, you can't unscramble it. That's entropy increasing. And that, for many scientists, is the source of time's direction. But here's where things get tricky. That rule about entropy, it's statistical, not absolute. It just means disorder is more likely than order, not that the reverse is impossible. Theoretically, it's not against the laws of physics for a cup to reassemble itself. It's just so unlikely that it may never happen once in the lifetime of the universe. But the laws allow it. In other words, entropy increasing isn't a fundamental law in the same sense as gravity or electromagnetism. It's more about probabilities than certainties. Even more confusing is this. If the universe started in a highly ordered, low entropy state, like at the Big Bang, why did it start that way? Why didn't it begin in a messy, high entropy state if disorder is more probable? That's still an open question. Some researchers think the arrow of time is a result of that unusual beginning. The early universe was extremely compact, smooth, and low in entropy. As it expanded, there was more room for disorder to grow, so entropy increased, and time seemed to move forward. But that just kicks the question back a step. Why was the early universe so ordered to begin with? And this isn't just a theoretical curiosity. The arrow of time is tied to everything we understand about memory, causality, and even death. You remember the past, not the future. You cause something to happen, not the other way around. We all age in one direction. But if the fundamental laws don't enforce that direction, then something else must be shaping it. Could it be our perspective? Could the arrow of time be something that emerges only because of the way we process information? Some physicists and philosophers believe that's exactly what's going on. Our minds are information processing systems that build memories, detect patterns, and store events sequentially. And memory only works in one direction. You store information about what just happened, not what hasn't happened yet. That makes time feel like it's moving forward, but it might not be moving at all. The arrow of time could be something our brains create to keep track of change and make sense of cause and effect. It's less about physics and more about cognition. Now, let's add another twist. Some researchers have proposed that there might not be just one arrow of time. In isolated parts of the universe, or in different conditions, it's possible that the arrow could point in the opposite direction. That might sound crazy, but it actually fits with what we know about entropy. If you have two systems isolated from each other, each could have its own arrow depending on its starting conditions. In fact, some cosmologists have speculated that the universe might contain regions where time runs backward from our point of view, where beings there would remember what we call the future and forget what we call the past. That's not science fiction, it's a real possibility allowed by the equations. It's also worth noting that time gets even messier in quantum mechanics. Some interpretations of quantum theory suggest that events don't become real until they're observed. That leads to strange situations where the future can affect the past, depending on how an experiment is set up. These are edge cases, and they're still being debated, but they show how unstable the arrow of time really is when you dig into the foundations. So what does all this mean? It means the direction of time, the one-way street we all assume is built into the universe, might not be fundamental at all. It might be an illusion created by a combination of probabilities, memory, and the specific conditions of our corner of the cosmos. The universe doesn't insist that time flows forward. That's just the way things seem from where we're standing. And if time isn't really pointing one way, then what exactly are we moving through? Quantum weirdness, time reversal, time mirrors, and why the future might already exist. So far we've seen that time might not flow, and the arrow we experience could just be a side effect of entropy and memory. But things get even stranger when you dive into quantum mechanics. Because down at the quantum level, the universe doesn't just blur the line between past and future, it practically erases it. The deeper you look, the harder it becomes to say whether time is even a useful idea at all. In fact, some experiments suggest that the future can influence the past, and others imply that time may not exist in the way we normally define it. If that sounds ridiculous, that's because it is, until you start seeing the data. Let's start with the basic weirdness of quantum mechanics. In the classical world, events follow a clear order. One thing happens, then another. But in quantum mechanics, particles don't seem to follow this logic. Instead of having definite positions or paths, particles exist in a cloud of possibilities, what's called a superposition. They don't settle into a specific state until something interacts with them, until they're measured. But when exactly does that measurement happen? And what determines the outcome? Now here's where it gets uncomfortable. The equations that describe these quantum systems don't have a built-in direction of time. Like in classical physics, they work just as well forward as they do backward. This means that, in theory, the future could influence the past just as much as the past influences the future. It's not how we normally think of cause and effect, but it fits the math. One particularly mind-bending example is the delayed choice experiment, an idea originally proposed by physicist John Wheeler. In this setup, a particle is sent toward a detector that can either measure which path it took or whether it created an interference pattern, essentially asking whether it behaved like a particle or a wave. But here's the twist. The decision of how to measure the particle is made after it has already passed through the apparatus. And somehow the particle's earlier behaviour changes depending on that future choice. It's as if the particle knows how it's going to be measured and adjusts its past behaviour accordingly. That's not just theoretical anymore. Variations of this experiment have been carried out, and the results are consistent with quantum predictions. It seems the future choice affects what happened in the past, or at least the past isn't fully determined until the future measurement takes place. And this breaks our normal idea of time. It suggests that past and future might be entangled in ways we can't understand yet. Then there's another set of experiments involving what researchers call time mirrors. These involve creating special conditions, often using carefully tuned electromagnetic waves, where waves are forced to evolve in reverse. This isn't just running a video backward, it's creating a real-time system where, under the right setup, the waves retrace their previous path back to the source. Some physicists believe this could provide insight into how time symmetry might work in the physical world. If we can create controlled environments where systems evolve backward in time, even temporarily, it hints that the laws of physics don't forbid time reversal. They just require very specific conditions. This becomes even more fascinating when you consider quantum entanglement. When two particles become entangled, their properties are linked in such a way that measuring one instantly affects the other, no matter how far apart they are. And again, this effect appears to work outside of time. It doesn't matter which particle you measure first. The correlation between them holds, even if one is measured before the other, or vice versa. That leads to interpretations where time isn't really a factor in how information is shared between entangled particles. It's like the universe is treating time as optional. Now, not all physicists agree on what this means. Some say it's just a quirk of measurement. Others argue it points to something deeper. That time itself might emerge from entanglement. There's even a theory called the Page-Wouters mechanism that tries to explain time as a side effect of quantum entanglement. In this view, the universe as a whole is timeless. It's just a giant, unchanging quantum state. But from within that state, subsystems can experience time because of their entanglement with other parts. In other words, time is something that appears when you look at part of the universe from the perspective of another part. But overall, nothing is actually moving. Everything just is. This interpretation doesn't just challenge how we think about time, it questions whether time even exists as a fundamental thing. It suggests that time, like temperature or pressure, might be an emergent property. Not a core feature of reality, but something that appears when you look at complex systems from a particular angle. And if that's true, then the future doesn't come from the present. It's already there, all of it, past, present, future, is encoded in the total structure of the universe. We just don't have access to most of it. We experience one slice at a time, like flipping through pages of a book we can't see the end of. But that doesn't mean the end doesn't exist, it just means we're not there yet. Of course, this doesn't mean we can hop into the future or send messages back to ourselves in the past. Entanglement and time symmetry don't allow for that kind of communication. But they do suggest that time might not be a one-way road. It might not even be a road at all. So now we're left with a weird picture. Time isn't flowing. It doesn't have a preferred direction. And it might not even exist until we observe it. That doesn't match anything we were taught growing up. But it matches what we see in the lab, and that's what makes quantum weirdness so important. It doesn't just bend the rules, it breaks the most basic one we all assumed was solid. That time is a simple, linear thing, moving from one moment to the next. It's not, at least not down here in the quantum world, down. If you want to understand how strange time really is, don't just look at space or black holes or particles. Look at the clocks. Because even the way we measure time has changed over the years. Not just in technology, but in definition. We've gone from tracking the sun across the sky to counting vibrations in atoms. And now, scientists are getting ready to redefine what a second even is. That might sound like a technical update, something only metrologists care about. But when you understand why this change is happening, you start to realize that even timekeeping, something we think of as solid and absolute, is surprisingly flexible. Let's go back. For most of human history, people measured time by observing the sky. Days were based on the rising and setting of the sun. Months followed the moon. Years followed the seasons. These cycles were practical, but not very precise. Timekeeping improved with the invention of mechanical clocks in the Middle Ages, then pendulum clocks, and eventually quartz watches. Each of these was more accurate than the one before, but they all still relied on something moving in regular intervals. That's the key idea behind any clock. Find a system that does something consistent, over and over, then count those repetitions. In 1967, we made a leap. Scientists redefined the second, not in terms of the Earth's rotation or the movement of stars, but using atoms specifically, the cesium-133 atom. They discovered that when cesium atoms are exposed to microwave radiation at just the right frequency, they flip between two energy states. This flip happens incredibly consistently, 9,192,631,770 times per second. So they defined 1 second as the time it takes for that many oscillations to occur. That became the official global standard. It's how your GPS, your phone, and even stock market trades keep time today. But that definition, as precise as it is, has limits. Cesium clocks are good, but they can still drift by about 1 second every 100 million years. That's impressive, but not perfect. And as our technology keeps advancing, those tiny errors start to matter. GPS satellites, for example, rely on hyper-accurate timing to determine your location. If the timing is off by just a fraction of a nanosecond, your position can be off by several meters. And when you're dealing with systems like quantum computers or deep space navigation, even that's not good enough. So now scientists are working on the next generation, optical lattice clocks. These use atoms like strontium or ytterbium and lasers that pulse hundreds of trillions of times per second. Because the frequency is so much higher than cesium, the measurement becomes more precise. Think of it like using a ruler with millimeter markings instead of centimeters. You get more detail. These new clocks are so precise, they would only lose or gain 1 second over the entire age of the universe. The international scientific community is preparing to redefine the second again, this time based on one of these optical transitions. The decision hasn't been finalized, but it's expected within the next few years. Once that happens, we'll be using an entirely new physical process to measure time. That doesn't mean the second will feel different. Your watch won't change. But on a deeper level, the shift reveals something important. Time, as we define it, is tied to physical systems we choose. It's not something that exists separately from those systems. It's a human construction, based on what we can measure and what we choose to measure. That realization has massive implications. If time is defined by oscillations of atoms, and we later switch to even more precise atoms or methods, then what does that say about time itself? Is it an independent reality, or just a set of rules we build around consistent patterns? And what happens when we reach a point where those patterns start to break down, like near black holes, or during the first split second after the Big Bang? Our definitions of time rely on stability, but the universe isn't always stable. Even now, we're starting to see how timekeeping's branching into new territory. Some of these new clocks are so sensitive, they can detect gravitational differences just by being moved 1 centimeter higher. That means you could place 2 clocks at the bottom and top of a staircase, and they tick at different rates, just because of the slight difference in gravity. Not a theory, this has been demonstrated. Time, it turns out, really does tick differently, depending on where you are. This is more than a cool fact. It means our most accurate clocks are starting to show us what Einstein predicted, that time isn't universal. It bends, it stretches, it changes based on speed and gravity, and the more accurately we measure it, the less solid and reliable it seems. Instead of revealing a clear, uniform rhythm to the universe, we find that time is messy, it's local, it's relative, and we're still just scratching the surface. The shift in how we define time isn't just a matter of scientific housekeeping, it's a sign that our understanding of time is still evolving. We used to think of time as something absolute, a ticking metronome running in the background of reality. But the better our tools get, the more we realize that there is no one single clock behind everything. Time is not a fixed stage, it's part of the machinery. And even the most precise second we can measure is only as stable as the atoms we build it on. So the next time someone tells you there are 60 seconds in a minute, or that a second is always a second, just remember, that's only true because we agreed to make it true. The universe doesn't care. Time, as far as the cosmos is concerned, is whatever we say it is, and we're still figuring out what that really means. So far we've been talking about time as physics sees it. But here's something most people forget. The experience of time isn't controlled by physics, it's constructed in your brain. The ticking of a clock, the feeling that time is rushing by or dragging on, the way you remember the past but not the future, all of that happens inside your mind. And when neuroscientists study how the brain processes time, they find something strange. Your brain doesn't track time the way a stopwatch does. It invents it. It builds time as a story. First, consider how memory works. You can only remember the past. That seems obvious. But it's the foundation of how we even know what time is. If your memory stopped working, time would vanish. You wouldn't know what just happened. You wouldn't have a concept of sequence. Every moment would feel disconnected, like an endless present. Memory gives us the illusion that the past is behind us and the future is ahead. But here's the catch. Memory isn't a perfect recording. It's not like a video camera. It's more like a reconstruction. Your brain doesn't store every detail of every second. It saves pieces, snapshots, patterns, impressions, and then reassembles them when you try to recall them. That reconstruction happens in the present, using neural circuits designed not just for memory, but for prediction. The same parts of your brain involved in remembering the past are also used to imagine the future. This has been demonstrated in brain imaging studies. When people are asked to recall a memory or imagine a future event, the same regions of the brain light up, especially in the hippocampus and parts of the prefrontal cortex. This has led some researchers to propose that what we call mental time travel is really just one function, the brain navigating a mental timeline that doesn't actually exist outside of thought. In other words, your past and future are both generated in the same way, using the same internal mechanisms. The only difference is that you treat one as real and the other as hypothetical. This explains a lot about how subjective time can be. Think about how time feels different depending on what you're doing. When you're bored, it drags. When you're engaged or distracted, hours can vanish in what feels like minutes. And when you're afraid, like in a car crash or during a fall, time seems to slow down. But studies show that this isn't because you're processing more information in the moment, it's because you remember it differently. Fear enhances memory formation, making you think more happened than actually did. It creates the illusion of slowed time, but only after the fact. Then there's the weird experience of time during traumatic events or altered states of consciousness. People who have had near-death experiences, intense meditation sessions, or even used certain drugs often report that time disappeared, stopped, or became meaningless. This suggests that time perception isn't just distorted, it can be completely turned off, depending on how your brain is operating. Even in daily life, your brain constantly compresses and edits your timeline. It's been shown that people are more likely to remember events that are emotionally intense, novel, or attention-grabbing. Meanwhile, routine activities often vanish from memory. This means your sense of how much time has passed isn't based on the clock. It's based on how many meaningful, mental events your brain can recall. That's why childhood summers feel longer in memory. Your brain was recording new things all the time. As adults, when days blend together, time seems to vanish. The clock didn't speed up. Your memory just didn't think those moments were worth saving. And during the COVID-19 pandemic, many people experienced this firsthand. The lack of novelty, the blurred routines, the sameness of each day. It all made time feel strange. Some people felt like the year disappeared. Others said it felt like it never ended. Again, nothing changed about time itself. What changed was how our brains processed events. Another layer to this is attention. When you're focused on time, like watching a timer or waiting for a file to download, it feels longer. But when your attention is elsewhere, time seems to slip past unnoticed. This shows that time perception isn't passive. It's something the brain actively generates based on what it's paying attention to. Even the idea of a present moment is a brain construct. Your brain needs time to process sensory information. Light, sound, touch. That means what you experience as now is already a little bit delayed. Some researchers estimate that your conscious awareness lags behind real events by about half a second. To keep everything feeling smooth and connected, your brain stitches inputs together into what it decides is a present moment. That moment is fake, but it's convincing. There's also research into what are called time cells in the brain, neurons that fire in patterns that seem to encode the timing of events. These cells are thought to help us understand sequences, durations, and when something occurred relative to something else. But even here, the system isn't built to track time like a machine. It's approximate. It's context dependent. It works well enough for making sense of cause and effect, but it's flexible and error prone. It tells us that the brain doesn't care about measuring time, it cares about interpreting it. So what does all this mean? It means that time isn't just warped by gravity or motion, it's warped by thought. Your experience of time is shaped by how you remember, what you notice, what you care about, and how your brain chooses to represent change. Time isn't something you sense directly like light or sound. It's something your brain infers from pattern and builds into a coherent story. A useful story, yes, but a story nonetheless. When people say time flies when you're having fun, they're not just being poetic. They're pointing to a real, measurable difference in how the brain encodes and reconstructs experience. And once you understand that, you have to ask, if the past is just memory and the future is just imagination, then what part of time is actually real? And that question has no simple answer. We've seen how physics breaks the rules we thought time followed. We've seen how the brain plays a big role in shaping our experience of it. But there's one more layer that doesn't get talked about enough. Culture. The way we experience time isn't just influenced by biology or science, it's also shaped by the society we grow up in, the language we speak, the metaphors we use, the stories we're told as children. All of it leaves an imprint on how we think about the past, the future, and what it even means for something to happen in time. Let's start with something simple: direction. In English, we talk about the future as being ahead of us and the past as behind us. We say we're looking forward to the weekend or putting something behind us. These metaphors feel natural if you grew up speaking English, but they're not universal. Some cultures imagine time very differently. For example, the Aymara people of South America reverse that orientation. In their language, the past is in front of them and the future is behind. Why? Because the past is known. You can see it, just like you can see what's in front of you. The future is unknown, invisible, like what's behind your back. Then there are the Pormpuraaw people of Australia, whose sense of time isn't based on the body at all, but on cardinal directions: north, south, east, and west. For them, time flows from east to west. So if they're facing north, the future might be on their right. If they turn around, the future is now on their left. They don't think of time as tied to the self, but to the environment. That's not just a linguistic curiosity. It affects how they process events, how they tell stories, and how they think about memory. Even the grammar of a language can shape how we think about time. In English, we mark time very explicitly. We say things like, I will go, I am going, or I went. There's a clear distinction between past, present, and future. But some languages don't work that way. In Mandarin Chinese, for example, the same verb form can be used for past or future. Context fills in the details. This doesn't mean Mandarin speakers are confused about time. It just means they don't separate it into clean boxes as often. Some researchers believe this subtle difference influences how people plan, save, and even think about responsibility. There's some evidence that people who speak languages with less rigid time distinctions tend to be more future-oriented in their decisions. These cultural differences aren't just theoretical, they show up in real-world behaviour. In some cultures, punctuality is treated as essential. Being 5 minutes late is seen as disrespectful. In others, time is more flexible. The event starts when people arrive. Deadlines are suggestions. The clock is there, but it's not in charge. Neither system is more correct. They just reflect different ways of organising life. Even our concepts of ageing, history, and death are shaped by culture. In the West, we often think of time as linear. You're born, you grow up, you work, you retire, you die. It's a straight line, with progress as the goal. But in many indigenous cultures, time is seen as circular. Life, death, and renewal are part of a repeating cycle. The ancestors are not gone, they exist in a different part of the cycle, still influencing the present. This changes how people think about memory, legacy, and responsibility. Think about how this affects daily life. If your culture sees time as a limited resource, something you can waste or run out of, you're likely to feel constant pressure to be productive. If your culture sees time as a cycle, you might approach problems more patiently, knowing things will come around again. It's not that one approach is better, but the way time is framed influences how people deal with stress, goals, and even relationships. Technology has added another layer. In industrial societies, we divide time into hours, minutes, and seconds. But these divisions aren't natural. They're tools we invented. Before mechanical clocks, people used sun position, seasons, or natural events to track time. Days weren't carved into 24 equal slices. Instead, the length of a workday changed with the light. The invention of clocks made time feel uniform, objective, and external. But it also disconnected people from natural rhythms. In digital culture, that disconnect is even stronger. Notifications, deadlines, countdowns, and real-time updates make us treat time as a commodity, something to manage, optimize, and monetize. But in doing so, we often ignore the deeper truth. The experience of time is still personal, cultural, and subjective. No app can measure how long a moment feels. So what's the point of all this? It's to show that time isn't just one thing. It's not a single concept with one meaning. It's a patchwork. Science, biology, and society each shape different pieces of it. And if you only look at time through one lens, whether that's a clock, a theory, or a cultural belief, you're only seeing a slice of the whole picture. Once you understand that, you start to see just how flexible time really is. Not in the sense that you can bend it like a sci-fi character, but in the sense that you're constantly bending it in your mind without realizing it. The language you speak, the values you were raised with, the tools you use, they're all shaping how time feels to you. And that feeling might be very different for someone else, even if you're standing in the same place at the same moment. Because in the end, time isn't just measured by what happens, it's measured by how we understand it. And that understanding, it's never been the same for everyone. The more we examine time, the more it begins to look like something built on top of something else. Not a fundamental ingredient of reality, but something that emerges from deeper, more basic laws. This idea might sound abstract, but it's becoming one of the most important questions in modern physics. Could it be that time is not built into the fabric of the universe at all? That it's something that only appears when you zoom out far enough, when you have matter, change, and complexity? To understand what emergent means, think of temperature. On a microscopic level, temperature doesn't really exist. What you have are particles, atoms or molecules, moving around with different speeds. Temperature is just a way of describing the average motion of all those particles. It's a useful concept, but it's not fundamental. You can't point to a single particle and ask what its temperature is. You can only talk about temperature when you look at the system as a whole. Some physicists believe time works the same way. One of the most well-known ideas in this direction comes from the Page-Wouters mechanism. It's a proposal that, on a deep quantum level, the universe doesn't evolve in time at all. Instead, it exists as a static quantum state, something that just is. But if you look at parts of the system relative to other parts, you start to see change. You start to see sequences, correlations, and even something that looks like a clock ticking. In other words, time appears when you focus on the relationship between subsystems. But globally, nothing is changing. The universe as a whole is timeless. This isn't just a weird idea buried in a paper somewhere. It's been tested in lab-scale quantum systems. Physicists have built tiny quantum setups where the Page-Wouters model actually plays out. The system as a whole doesn't evolve, but when you zoom in on one part and treat another part as a reference, a sense of time starts to emerge. It's like two clocks that don't tick unless you compare them to each other. Another place where this question comes up is in the search for a theory of quantum gravity. Right now, our best descriptions of the universe are split. We use general relativity for the large-scale stuff, planets, stars, galaxies, and we use quantum mechanics for the small-scale stuff, atoms, particles, and fields. Both theories are extremely successful, but they don't play well together. And one of the biggest sticking points? Time. In general relativity, Time is part of the geometry of space-time. It bends and stretches. It depends on motion and gravity. But it's always part of the stage. In quantum mechanics, time is just a parameter, something that ticks away in the background. It's not dynamic. It doesn't interact with the system. This mismatch creates what physicists call the problem of time. When they try to merge the two frameworks, say, to describe the early universe or the inside of a black hole, time seems to disappear from the equations. The result is something that looks like a timeless, frozen system. But we obviously experience time. So where is it? This has led to the idea that time, like space, might be emergent. Not something that's always there, but something that comes into play once certain conditions are met, like a particular configuration of particles or a certain level of complexity. Time, in this view, is not a starting point. It's a side effect. Some proposals go even further. There are theories that suggest space-time itself, both space and time, emerge from something even more abstract, like entanglement or quantum information. These models treat the building blocks of reality not as particles or fields, but as relationships, patterns of correlation. You don't start with a grid of space and a flowing clock. You start with a web of information, and from that, space and time take shape. It's like building a video game. You don't need to simulate space and time directly. You just need rules and interactions, and space and time come out of that. This isn't just theoretical hand-waving. There's growing interest in things like holographic principles and quantum computational models of the universe. These frameworks hint that what we experience as a smooth flow of time might actually be the result of a deeper process, like pixels on a screen or bits in a computer. Time is what it looks like from the outside, but underneath, it could be something else entirely. Here's another way to think about it. Imagine you had a universe that was completely frozen. No motion, no ticking clocks, no change at all. If you were somehow embedded in that system, and you looked at different parts of it from different perspectives, you might start to infer a timeline. You'd see patterns that suggested before and after. You'd see traces of what you'd call memory. You'd reconstruct a story that includes a past and a future. But the system itself never changed. The timeline was something you imposed on it based on structure, not dynamics. This changes how we think about what's real. If time is emergent, then it's not part of the ultimate foundation. It's more like a useful shortcut, a way of summarizing how complex systems behave. That doesn't mean it's fake, it just means it's not fundamental. Like temperature or pressure or even color. It's a description that works at a certain level, but disappears when you go deeper. And that has huge implications. If time is emergent, then asking what happened before the universe started might not make sense. If time only appears when the universe reaches a certain complexity, then there was no before. Just like there's no north of the North Pole. Time might have a starting point, not because something happened first, but because that's where the conditions for time to exist were finally met. So when we ask questions like what is time, or where does time come from, we might be asking them backwards. Maybe the better question is, under what conditions does time appear? What does the universe need to be doing before we can even talk about time? And if those conditions aren't met, if you go deep enough, small enough, or early enough, then maybe there's just no time at all. After everything we've seen, time not flowing, the past and future possibly coexisting, our sense of time being shaped by memory, culture, and even quantum processes, one big question remains. If all of time already exists, then are we really choosing anything at all? Do we have free will, or are we just following a script that's already written? It's a hard question, and it makes people uncomfortable, but it's unavoidable once you start questioning what time really is. Let's go back to the block universe idea from relativity. In that model, all moments, past, present, and future, exist simultaneously in a four-dimensional structure. Your birth, your final breath, and everything in between are just locations in space-time. You're not moving through time, you just exist at different coordinates. This model doesn't allow for a flowing now, and it doesn't leave room for the future to be uncertain. From this perspective, the future is just as fixed as the past. We just haven't experienced it yet. If that's true, then what happens to free will? If the future already exists, can we really say we're making choices? Or are we just watching the movie of our lives play out, frame by frame? with no real control. Some physicists and philosophers say yes, we're just observers. They argue that everything we're going to do is already there in the fabric of space-time. The feeling of choice is just that, a feeling. Your decision to have coffee instead of tea this morning wasn't really a choice. It was always going to happen that way. You were always going to sit where you're sitting right now, reading these words. Every thought you have, every move you make, it's already baked into the structure of the universe. That sounds bleak. But it's not the whole picture. There's another way to look at this. Even if the future exists in the block universe, that doesn't mean it was determined by the past in the way we usually think. Determinism, the idea that every event is caused by prior events in a predictable way, isn't a requirement of the block universe. It just means everything exists. It doesn't tell you why it exists or what caused it. And in quantum mechanics, determinism gets blurry. There's fundamental randomness built into the system. You can't predict the exact outcome of a quantum event. You can only calculate probabilities. So even if the future exists, it may not be determined in the classical sense. More importantly, even in a block universe, you still experience choice. Your brain goes through the process of evaluating options, thinking, deciding, and acting. That process is real. It happens inside your mind based on the information you have, your values, your goals, and your perception of consequences. Whether that experience is happening in a universe where the future is already written doesn't change the fact that the experience is happening. Think of it this way. A character in a novel doesn't know what's going to happen on the next page. From their point of view, every decision feels real. They weigh their options, they struggle, they grow. But from your point of view, the reader looking at the whole book, the story is already complete. That doesn't mean the characters' choices weren't meaningful. It just means they exist within a structure, where the whole timeline is already mapped out. Some philosophers argue that this view doesn't eliminate free will, it just reframes it. They call it compatibilism. The idea is that free will isn't about defying the laws of physics or escaping causality. It's about acting in accordance with your own reasons and motivations without being forced. If your choices come from you, your values, your thoughts, your desires, then they're still your choices, even if those choices are embedded in a larger structure. And from a practical point of view, we have no access to the future. We can't see it. We can't know it in advance, so, as far as we're concerned, it's open. We live moment to moment, making decisions based on what we know, hoping for certain outcomes, adjusting as we go. That process, deliberation, action, consequence, is how we experience agency. Whether or not the future is already there doesn't change how we move through life. In fact, the idea that everything's predetermined can actually make your decisions feel more significant, not less. If your future actions are already encoded into space-time, then they still matter. You still play a role in shaping the version of the universe that exists. Your actions don't vanish because they were predictable. They're still part of the structure. Your courage, your effort, your kindness, your mistakes, they're all real. They're all part of the record. But let's be honest, no theory of time or free will fully satisfies everyone. Some people find comfort in determinism, believing everything happens for a reason, even if that reason is buried in physics. Others find it oppressive. Some believe we're free agents in an open universe, carving out our own paths with each decision. Others think we're just riding the rails of a cosmic script. The truth is, we don't know. Physics hasn't answered this yet. Philosophy hasn't settled it. Neuroscience is still working on it. But what we do know is this: our experience of time and choice is real. We live inside a story that feels like it's unfolding. We face real uncertainty, real decisions, and real consequences. And whether that story is fixed or flexible, it's still ours. In the end, maybe asking if we have free will is the wrong question. Maybe the better question is, what are you going to do with the time you've got, even if it's already written? We've gone through physics, neuroscience, culture, and philosophy. We've seen that time doesn't behave the way we were taught. It doesn't flow. It doesn't tick at the same rate for everyone. It's not even clear it exists at the smallest scales of the universe. We've found that time is relative, messy, shaped by memory, defined by convention, and possibly not even fundamental. But after all of that, the big question still hangs in the air. So what is time really? Here's the hard truth: we don't know. That might sound like a disappointing answer, but it's the most honest one. the best minds in science still don't agree on what time actually is. Some think it's a dimension, like space. Some think it's an illusion. Others think it's emergent, or even a side effect of entropy, or entanglement, or consciousness. And each theory works well in its own domain. Relativity works on the large scale. Quantum mechanics works on the small scale. But there's no single unified picture that explains time everywhere, all at once. Every time we try to pin it down, it slips through our fingers. In math, we treat it like a parameter. In our lives, we treat it like a resource. In our minds, we treat it like a story. None of these definitions are wrong, but none of them are complete either. The more precisely we try to define time, the more it seems like we're chasing a shadow. We can measure intervals. We can track change. We can build clocks that keep time to 15 decimal places. But the deeper question, what is this thing we're measuring, keeps getting harder to answer. And maybe that's the point. Maybe time isn't a thing you can isolate. Maybe it's not a single object in the universe, but a relationship between events. Maybe it only makes sense when something changes, when information moves, when one thing depends on another. Maybe time is the language we use to describe difference. Before and after. Cause and effect. Memory and anticipation. And when you think about it that way, time starts to feel less like a thing and more like a structure, a way we organize our understanding of reality. It's not some invisible river flowing past us. It's a framework we build to track motion, thought, and meaning. It's how we make sense of the fact that things change. So yes, everything you know about time might be wrong, but that's not a failure of understanding, it's progress. Because the real story of time is still being written. We're only just starting to see how complex it is, how deeply it's tied to everything else. Space, matter, energy, information, even consciousness. And that means the mystery of time isn't a dead end, it's an open door. Because if time is still an open question, then maybe, just maybe, we still have time to figure it out. After all the strange and complicated things we've covered about time, how it might not flow, how the past and future may already exist, how clocks measure it differently in different places, how the brain invents it, how culture shapes it, and how science still can't quite define it. You might be wondering, so what? Why does any of this matter? It matters because we live our entire lives wrapped around the idea of time. We're constantly planning, remembering, regretting, rushing. We divide our lives into decades. We worry about wasting time. We try to manage it, save it, invest it, race against it. Time is the most important thing we think we have, and yet, the deeper we look, the more it seems like we've misunderstood it from the very beginning. If time isn't what we thought, then maybe the way we live can change too. Think about how much stress is tied to the feeling that time is running out, that there's never enough, that we're falling behind, that we're too late. But what if time isn't a fixed arrow we're stuck on? What if it's more like a map, a landscape of moments that all exist even if we can't reach them yet? That doesn't make life less meaningful. If anything, it makes every moment more precious. Because if every moment exists forever, then how we act inside each one still matters. Not because we're racing towards some finish line, but because every moment is its own place on the map of existence. And if the brain invents time through memory, that means we have more power than we think. The way we experience time can be shaped. It can be stretched, slowed, focused. Being present isn't just a slogan. It's a kind of resistance against the illusion that everything is slipping away. When you stop chasing the next thing and pay attention to this moment, you're doing something radical. You're stepping off the timeline, even if just for a second. This matters in science too, because time touches every part of physics, from the birth of the universe to the decay of particles. If we don't understand time, we don't really understand anything. And the fact that time breaks down in our best theories is a clue that something big is still missing. Something we haven't seen yet. The search for time's true nature might be the key to unlocking the next big shift in how we understand reality. Just like Einstein's theories changed everything a century ago, it matters in philosophy. Because if time isn't fundamental, then neither is causality in the way we normally picture it. The way we think about free will, morality, identity, all of that is tied to how we imagine time works. If the past and future are more connected than we realise, if the future is already there, if choice is a part of a bigger structure, We may need a new way of thinking about responsibility and meaning, and maybe it even matters emotionally. Whether or not time flows, we do. We grow, we learn, we change. Our memories shape us, our hopes pull us forward, and no matter what physics says, we all live as if time matters. Because it does to us. So no, this isn't just a science story, it's a human story. Because at the end of the day, understanding time better doesn't take the magic out of life. It puts more of it in. It shows us how little we know, how much we still have to discover, and how strange and beautiful it is that we get to experience time at all. That we get to be here, in this moment, whatever that means.